We've re-recorded this talk because of technical difficulties during the original talk. The title of my talk is Bohmian Trajectories as the Foundation of Quantum Mechanics and Quantum Field Theory. I'd like to say thank you very much to the organizers of this conference for inviting me here. It's a great honor for me to speak at a conference on the occasion of the 100th birthday of David Bohm. I'd like to say happy birthday, David Bohm. I myself have never met David Bohm. When he died, I had just enrolled in university. In 1952, David Bohm did an absolutely cool thing. He solved the biggest of all problems in quantum mechanics, which is to provide an explanation of quantum mechanics. His theory is known as Bohmian mechanics, or pilot wave theory, or the de Broglie-Bohm theory, or the ontological interpretation. I will use these names synonymously. I will mainly say Bohmian mechanics because that's what I'm used to. This theory makes a proposal for how our world might work. It agrees with all empirical observations of quantum mechanics. Unfortunately, it is widely underappreciated. It achieves what was often claimed to be impossible. It was claimed before 1952 to be impossible. It was even claimed after 1952 to be impossible. That is, to explain the rules of quantum mechanics through a coherent picture of microscopic reality. This theory is remarkably simple and elegant. I find it very convincing. In my mind, it is probably the true theory of quantum reality. Compared to Bohmian mechanics, orthodox quantum mechanics actually appears quite unprofessional, as John Bell said, and incoherent, as Albert Einstein said. In fact, orthodox quantum mechanics appears like the narrative of a dream whose logic doesn't actually make sense anymore once you are awake, but seemed completely natural while you were dreaming. According to Bohmian mechanics, electrons and other elementary particles are particles in the literal sense, that is, material points, which at every time have a particular location in space. So over time, they move along some trajectory in space. So I will denote their position by Qj of t. So bold-faced letters will mean vectors in R3. J is the number of the particle number j. These trajectories are governed by Bohm's equation of motion, which I will show to you on the next slide. And in view of the claim that it was impossible to explain quantum mechanics through any coherent picture, it is quite remarkable that something as simple as particle trajectories would suffice to actually give an explanation of quantum mechanics. You might have thought that something very complicated and very non-obvious would be needed to find such an explanation that so many people had looked for so many years. So, in the end, what went wrong in orthodox quantum mechanics? That's very simple. Some variables were left out of considerations, and these variables were the particle positions. On this slide, I've collected the basic laws of Bohmian mechanics, so I'm giving you a definition of the theory. First law is the equation of motion, Bohm's equation of motion for the particles. So it's a first-order differential equation for the Qj. The right-hand side involves a wave function psi, and the second equation is the time evolution law for the wave function, which is the ordinary Schrödinger equation that we know. The third law says that the initial configuration of this Bohmian system or Bohmian universe is random with probability density given by psi squared, with psi the wave function, the initial wave function. From this, together with the equation of motion and the Schrödinger equation, it follows that, in fact, at any time t, the probability density of the configuration is given by psi t squared, with psi t, well, the wave function at time t. So here's an example of how Bohmian mechanics then explains the results of quantum mechanics for the double slit experiment. So what is shown here is a collection of a number of alternative possible Bohmian trajectories. So the particle follows one of these trajectories. These trajectories are roughly psi square distributed. So you can see that in some regions, more trajectories arrive than in other regions, and therefore the particle is more likely to arrive in those dark regions with many trajectories here than in those bright regions in between. So in every run of the experiment, one particle passes through this setup, arrives at some spot on the screen. The spot is psi square distributed. The wave propagated through both slits. The particle went only through one slit. In the end, you get a distribution of spots on the screen that agrees with psi squared. Double slit experiment explained. John Bell wrote about that. This idea seems to me so natural and simple to resolve the wave-particle dilemma in such a clear and ordinary way that it is a great mystery to me that it was so generally ignored. Bohmian mechanics is clearly non-local. Let me explain that in terms of the equation of motion. You see here that the velocity of particle number j depends on the simultaneous positions of all other particles. So that's where you can directly see the non-local dependence. So this morning, Jan showed us some quotation from Esfeld suggesting that he thinks that Bohmian mechanics is local. I don't understand what Esfeld had in mind when he wrote that. So there's no doubt that Bohmian mechanics is non-local. Bohmian mechanics avoids the problematical idea that the world consists only of wave function, and in fact also makes it more easily visible how problematical actually this idea is, because Bohmian mechanics makes it visible that three-dimensional physical objects like trees and chairs are actually made of these particles and are not made of wave function. Bohmian mechanics provides precision, clarity, a clear ontology in space-time. The precision, you see, I gave you the definition, the full definition of the theory on the previous slide. 3 laws, that's it. Clear equations, clear ontology. Bohmian mechanics allows for an analysis of quantum measurements, thus replacing postulates of orthodox quantum mechanics concerning measurements by theorems. Now, in this talk, I'd like to say something about extensions of Bohmian mechanics, particularly about particle creation and about relativistic space-time. Concerning particle creation, now I mainly report about work by Bell in 1986 and some further development of that I was involved. The natural extension of Bohmian mechanics to particle creation involves a setting in which a variable number of particles is possible. So the Hilbert space would now be Fock space, which is an orthogonal sum of Hilbert spaces corresponding to all different possible numbers of particles. A vector in Fock space can be represented as a wave function, a function on the configuration space of a variable number of particles. And this configuration space now would be the union, the disjoint union of configuration spaces for every possible particle number. So here I've drawn some scenario of what particle creation and annihilation looks like in a setting with particle trajectories. So picture A here on the left-hand side, this is a space-time diagram. We have here a situation of, let's say, 2 electrons. At some point, 1 electron emits a photon. Then the photon moves over to the other electron where it gets absorbed. So in a scenario with the particle emission and absorption, world lines can begin and end. Good. So that means that at some times you have 2 particles, at later times you have 3 particles, even later times you have 2 particles again. Now the picture B here shows a case that could perhaps be a situation of a photon decomposing into an electron-positron pair. Good. Let's focus on picture A. Now here's a situation, here's what that looks like in configuration space. So configuration space, as I said, the configuration space of a variable number of particles is a union of different sectors corresponding to different particle numbers. So I've drawn here the first 4 sectors, the 0 particle sector, the 1 particle sector. I've drawn it for 1-dimensional physical space, the 2 particle sector, the 3 particle sector. Good. Now this picture, the space-time diagram, this picture of the world lines, translates into the following motion of the configuration in configuration space. We start here with the 2-particle configuration, which kind of moves around in configuration space as time proceeds. At a certain time, namely the time at which the third particle gets emitted, the configuration jumps from the 2-particle sector to the 3-particle sector. Good. Then it continues moving around in the 3-particle sector. So that's the time interval between this emission and the absorption event. Then at the time of absorption, the configuration jumps back from the 3-particle sector to the 2-particle sector, and then it will move around in the 2-particle sector of configuration space again. Good. So jumps necessarily have to occur in such a kind of picture. And in the theory that I'm about to describe, that extends Bohmian mechanics, including particle creation and annihilation, these jumps occur in a stochastic way. That is, they're intrinsically random. They occur at random times that are not predetermined. They occur perhaps to random locations that are not previously determined. So the idea here is that this theory is actually no longer deterministic. The spirit here is that it was fine that Bohmian mechanics is deterministic. That was simply the simplest theory you could come up with if you wanted to have a theory just for non-relativistic quantum mechanics with a conserved particle number. Now here we have a different setting. We want to have particle creation and annihilation. And then now the simplest and most natural theory is one that involves stochasticity, intrinsic randomness. Good. So now we also need a law that governs these stochastic jumps. What the law needs to prescribe is the rate, probability per unit time, of such a jump to occur. So for this, the theory has an equation that expresses the jump rate for a particular transition from one configuration to another as an expression in the wave function psi. Good. This rate you arrive at by considerations of simplicity and considerations of keeping the psi-squared distribution preserved. We want the configuration to be psi-squared distributed at all times. So here, we take the maximum with 0 of this quantity. That means the following. If this quantity is negative, then we take it to be 0. If the quantity is positive, we take this quantity. So the right-hand side is always greater or equal 0. You see here that it depends on the wave function psi. Here, HI is the interaction Hamiltonian, so I'm taking for granted here that the Hamiltonian is the sum of a free Hamiltonian and the interaction Hamiltonian, and these operators P of Q are the configuration operators, or, well, the appropriate version of position operators. That would mean for every point Q in the configuration space, that is, in the union of all these different sectors, any point there, the configuration operator could be, well, the appropriate projection to that point, or, well, that's not actually not well defined in case of a continuum. Rather, what it should be is you should integrate this over some region in configuration space. More generally, this P can be a positive operator valued measure on configuration space. Good. So this jump rate formula, that's the law that governs the jumps. In between the jumps, the configuration moves just according to Bohm's equation of motion. Then it follows mathematically that the configuration is psi squared distributed at every time t. The configuration is now a stochastic process. It's in fact a Markov process. So essentially the situation now is the following. If you give me a Hilbert space H, a state vector psi, a Hamiltonian H, a configuration space Q, and configuration operators P of Q, then we know how to set up this stochastic process, this Markov process, the Bohmian trajectories with jumps. Now, in this Bohmian theory with particle creation, it becomes visible that there is some unpleasant feature when you try to apply it to some serious Hamiltonians that come from quantum field theory. Namely, that's the ultraviolet divergence problem. So here's a simple example of that expressed in terms of a simplified model of a QFT, quantum field theory. Suppose we have two kinds of particles. I will call them X particles and Y particles. Suppose that the X particles can emit and absorb Y particles. And suppose for simplicity, we have only one X particle, and for even more simplicity, we assume it's just fixed at one location, let's say at the origin. Good. So the number of Y particles is still variable. They can be emitted at the origin or absorbed at the origin, and they can move around. Good. So here the Hilbert space is just the Fock space of the Y particles. For definiteness, suppose it's a bosonic Fock space, and the configuration space is just the configuration space of the Y particles. Now, when you try to write down what the Hamiltonian looks like for such a theory, let's say a non-relativistic Hamiltonian. So we're assuming here that the free Hamiltonian is just the Laplacian operator for the Y particles with some positive mass, my. Good. Now, the full Hamiltonian should have a further term responsible for creation and annihilation of particles. There's a kind of obvious way how you would write this term, how you would guess it. Okay, if you write it down in the particle position representation, which is what I want to do here because I want to use the... because I want to use I want to use it to define my Bohmian trajectories, so I want to have the wave function in the particle position representation. So here is what the equations then look like. recall that the wave function is a function on the union of these different sectors. So on each sector, it can be evaluated. So here we're using the n particle sector of the wave function because we're plugging in n points in R3. Here we're using the n plus 1 particle sector of the wave function because we're plugging in n plus 1 points. Here we're using the n minus 1 particle sector of the wave function because we've omitted one of the y particles. Good. So in these equations, you can see how the n particle sector now gets influenced by the n plus 1 particle and the n minus 1 particle sector corresponding to creation and annihilation of particles. What you see here is that from an n plus 1 particle configuration, by having one of the particles reach the origin, okay, you can that's when you want to jump to an n particle configuration. So that's why you connect here the wave function to a term that's in the n plus 1 particle sector with one particle at the origin. Likewise, here you take an n minus 1 particle wave function and you create the nth particle, which could have any label, any number from 1 to n, by giving it a delta function, that is, giving it a wave function concentrated at the origin to this new particle. Now, the problem with this kind of Hamiltonian, which is the Hamiltonian you would want to write down, is it's ultraviolet divergent. That means it's mathematically ill-defined. Such a Hamiltonian doesn't exist. It is infinite. Good. Now there's a standard way how you can deal with this situation, how you can make it finite. It's called an ultraviolet cutoff or a regularization. For this, you replace the delta function by some function that's not so extreme, a function that is perhaps also strongly peaked, but not infinitely strongly. So that means here's the place where we had the delta function in the previous equation. We replace it by this function phi, which is square integrable. Could look like this. Good. Then this function also appears in this other part to make sure the Hamiltonian is self-adjoint. So that now replaces inserting 0 for the last variable. Good. This move amounts to smearing out the x particle, giving it some charge distribution that has a positive radius, the radius being the size of this, the width of this function phi. Good. Well, this step already sounds a bit dubious because there's no empirical evidence for a positive radius of the electron. As far as we know, it can have radius 0. In this picture with Bohmian trajectories, there's another thing, another unpleasant feature that comes up, namely that then the y particles can be created and absorbed at a certain separation from the location of the x particle. Namely, they can be created and absorbed anywhere within this charge distribution, anywhere within the radius of the support of the function phi. So that means if we look at these particle trajectories closely, then we see that the absorption occurs not actually at the position of the x particle. The world line of the y particle ends at a certain distance from the x particle. Same thing with the particle creation. Good, that looks kind of, well, maybe it's a good approximation, but it looks like it's not serious. It's not the thing that we really want to have. So we'd like to get rid of that. This kind of ultraviolet problem can in fact be solved. Let me tell you how. The novel idea here is something that we call an interior boundary condition. So that's a kind of boundary condition on the wave function. The boundary here is a boundary to configuration space, and it's actually the set in configuration space where an x particle and a y particle meet. So for example, here I've drawn a situation, a part of configuration space. Let's say this is a sector of configuration space where only an X particle exists and no Y particle. Here's a sector of configuration space where one X particle and one Y particle exist. Okay, say in this scenario, this diagonal is the set where the X particle and the Y particle are at the same location. In this previous scenario, I fixed the X particle at the origin. Okay, then this boundary would just be the origin relative to the Y variable. Good. So now look at these two configurations that we want the creation or annihilation of a particle to connect. So let's say here's an X particle. Here's the configuration of an X particle and a Y particle at the same location. Now when we want to swallow the Y particle, we want the Y particle to disappear and the X particle to just stay at the same location. That's supposed to be this location. So we want jumps from here to there. The other way around for creation, if the X particle is at some location here, then we want to jump over here, that is, create a Y particle at the same location. So there are two configurations that are linked by this jump. And now this boundary condition links the values of the wave function at these two configurations. So it's of the following general form. The wave function, its n+1 particle sector on the boundary is related by some constant to the wave function on one sector below. Good. So more explicitly, let's say back in the example of the X particle fixed at the origin, then the boundary points are those which have one Y particle at the origin. Here, this notation, Y superscript n, is supposed to mean any configuration of n Y particles. Okay, so this is a 3 n-dimensional vector here. Good. So this is a configuration in the n+1 particle sector. Good. So here we're talking about the n+1 particle sector of the wave function. Good. So that on the boundary is fixed by some constant. So here's some example of what the constant could explicitly be. And here's the wave function one sector lower. So this is the boundary condition. This is now a condition that we require of the wave function. Now, actually, there's still one more complication here. I've written down what the precise boundary condition actually is. There's one more complication that comes from the fact that if you want to move a whole cloud of probability into one point, then the probability density has to go up like 1 over r squared as a consequence of that. Wave functions have to go up like 1 over r near the boundary. So since psi grows like 1 over r near the boundary, actually I want to extract the leading coefficient of the wave function here. So that's why I'm multiplying it by r to keep that finite. I'm taking the limit r to 0. That means I'm considering the limit in which I'm approaching the boundary. Good, but that's a detail. Essentially, that's the same thing as the boundary condition that I had before. Now, there's a particular choice of the Hamiltonian. You see here the last line is the same as we actually had in the original Hamiltonian. So is the first term here. The second term has been modified a little bit so as to make sure that actually all of the probability current into the boundary on the upper sector comes out again on the lower sector. So that overall probability is not lost, but just shifted from one sector to another sector. Good. Now, on a domain of wave functions that satisfy these boundary conditions, this Hamiltonian is actually well defined and is a self-adjoint operator. And that means there's no ultraviolet divergence problem anymore. So this Hamiltonian actually has the y particles created at the location of the x particle at the origin without any smearing out of the x particle or of its charge distribution. Good. So this can be proved, has been proved as a mathematical theorem. Let me make a remark here about the role of mathematical theorems in this context. You know, mathematicians love to prove things when they can, but often in physics, you don't actually need these proofs. You can do physics without having these proofs. Now, here the situation is a little different, because in this situation, the problem we had was that Hamiltonians were ill-defined, that they didn't actually exist. Good. And now we want to know whether this Hamiltonian actually really exists mathematically, whether it is well-defined, or whether it is still divergent. Now, this question can only be answered by a mathematical theorem that now actually guarantees to us that this Hamiltonian actually is well-defined, that it is self-adjoint, and in fact, it's also a positive operator. It's bounded from below. So this is a situation in which we actually need a mathematical theorem to be sure that we have no ultraviolet divergence problem anymore. Good. So we have such a theorem. Now, that means we have a unitary evolution in Fock space for these wave functions. Good. Now let's return to the Bohmian trajectories for that. So here we have the following rules. Between the jumps, the Bohmian configuration just follows Bohm's equation of motion within one sector of configuration space. As soon as this configuration reaches the boundary, that is, as soon as one of the y particles reaches the origin, the configuration will jump down one sector. That means we will take this n particle configuration, we will remove the one particle that has reached the origin and continue with n-1 particles. So that we will continue here in the sector of configuration space of n-1 particles. So this annihilation process, this jump, is actually deterministic. Now, if we want the theory to be time reversal invariant, we must also have the inverse process, the emission of a particle. Of course, we also want to have that. Now, for the emission of a new y particle at the origin, we actually still have a stochastic law that actually just follows from the when you analyze the time reversal invariance, then this law has to be stochastic. So that means that a new y particle gets created at a random time, and it gets emitted from the origin in a random direction of space with a rate. I have not written down the formula here. There is a formula for the rate. It's a rate that is dictated by the desire for time reversal invariance, together with the assumptions that the whole process should be a Markov process. Okay, yes. And the whole process should be a Markov process, and that the psi-squared distribution should be equivariant, should be preserved over time. Good. The next topic I want to talk about is different kinds of extensions of Bohmian mechanics, namely to relativistic space-time. In relativistic space-time, the situation is the following. If I am permitted to use a preferred foliation of space-time, foliation means a slicing of space-time into space-like hypersurfaces. Here, this diagram on the right is a picture of one possible foliation of space-time into space-like hypersurfaces. I will call this foliation the time foliation, and I will denote it by this letter script F. So if I can use a foliation as a preferred foliation, then there is a simple, convincing analog of Bohmian mechanics in this relativistic space-time. I will denote that by BMF, or Bohmian mechanics, with this given foliation. Good. So this theory, the equations for this were written down by Bohm and Hiley in 1993 for foliations that consist of parallel hyperplanes. So that corresponds to some fixed Lorentz frame by Dürr, Goldstein, Münch-Berndl, and Zanghi for curved foliations such as the one that I've drawn here, and they can also be generalized to curved space-time. Without a time foliation, no version of Bohmian mechanics is known that would make predictions anywhere near quantum mechanics, and I have no hope that such a version could be found in the future. So the situation that we have here is this. It seems it's against the spirit of relativity to grant a theory of a special foliation, a preferred foliation, such as this one. But I feel we should be relaxed about this. And it's a real possibility that our world is like that. So we should simply explore this possibility. It doesn't mean that relativity would be irrelevant. For example, in these equations of this theory, there is still a metric, g mu nu. The free Hamiltonian is still the Dirac operator. Formulas are still expressed with 4 vector indices, as in J mu. There is just also, in addition to these vectors and tensors that you have anyway, one more vector, the vector field n mu, that is normal to the time foliation in the metric G mu nu. So that's the unit, say the future pointing unit normal vector field to the surfaces of the foliation in terms of the metric G mu nu. Still, in this theory, despite the fact that it has a preferred foliation, there is no possibility of superluminal signaling. Good, so that's another thing that you might have worried. Also, I'd like to emphasize that the hypothesis of a time foliation, the hypothesis that there exists such a thing in nature, provides a very simple explanation of the non-locality required by Bell's theorem. Note also that a preferred foliation might be available anyhow. It might be provided by the metric. So here's a picture of a Friedmann, Lemaitre, Robertson, Walker space-time. And down here is the Big Bang. And in such a space-time, you could consider at every point in space-time the time-like distance from the Big Bang. So if our space-time, or consider any space-time that has a Big Bang, you could consider this function. It would be a bit like absolute time. Now consider the level sets of this function. So these would be the surfaces of constant distance from the Big Bang. They form a space-like foliation of the space-time. So just the metric can provide you with some preferred foliation. This metric has a preferred foliation. So why not use it for the Bohmian theory? Alternatively, a preferred foliation might be defined by the wave function. So proposals in that direction have been formulated by Dürr, Goldstein, Norsen, Struve, and Zanghi in this paper. Or another possibility, the foliation might be determined by an evolution law starting that could possibly involve psi, could depend on psi, starting from some initial time leaf, from some initial surface that's supposed to belong to the time foliation. Good. On this slide, I have the actual equations of motion. Let me not go into detail. Let me just mention one thing about how it works. We take here on some surface, on some time leaf, some surface belonging to the time foliation, we take the points where the different particle word lines intersect this surface. So that gives us a configuration on this surface. And that's where we will evaluate the wave function. So we take psi at this configuration. So we use this surface for defining a notion of simultaneity at a distance. Good. And that will then be used for determining the velocity of these particles or determining the directions in space-time tangent to the particle word lines. Good. So that's the structure of this equation of motion. Some key facts about this theory. First, it's still equivariant. That is, the psi-square distribution is still preserved. So in this case, that means that the configuration on the surface sigma will be psi-squared distributed for every surface that is part of the foliation. Now, on surfaces that don't belong to the preferred foliation, the actual distribution of the intersection point may differ from psi squared, but still, if you place detectors along that surface, then the detected configuration, the outcome of your detection experiment, will actually be psi squared distributed, even if this surface is tilted relative to the time foliation. That has something to do with the fact that the presence of the detectors, some of which are earlier in terms of the time foliation than others, will actually affect the wave function, will have the effect of an effective collapse of the wave function, and will therefore alter the intersection points of the other particles with this hypersurface. So in the present, it's still true then that actually the intersection points are psi-square distributed, but the intersection points in the presence of detectors are a little different from what they would have been in the absence of detectors. Now, as a consequence of the fact that detected configurations are just psi-square distributed, the foliation is invisible. That is, your experimental results actually reveal no information about which foliation was the time foliation, the preferred foliation. In fact, it follows further that all the empirical predictions of Bohmian mechanics with this special foliation agree with the standard quantum formalism and with the empirical facts. So, in fact, some part of this reasoning can be formulated as a theorem. So this theorem can be summarized as follows, as saying that if detectors are placed along any space-like surface sigma, then the joint distribution of the detection events is given by psi squared. The full a precise formulation of the theorem is more involved. You can read that in the paper. Good. So now this theory, Bohmian mechanics with the time foliation, is very robust. It works for an arbitrary given foliation f. It works even if the foliation has kinks, that is, if the surfaces are not smooth. It works even if the leaves of the foliation overlap with each other. It can be combined with the stochastic jumps for particle creation. It works also in curved spacetime. It works still if spacetime has singularities. So these are further reasons for thinking that this is a good law of motion for Bohmian particles in relativistic spacetime. I have said that for defining these extensions of Bohmian mechanics, it is useful to express the wave function in the particle position representation. Now, in relativistic space-time, if you express a many-particle wave function, or a wave function even more so for a wave function with a variable number of particles, if you want to express it in the particle position representation, then an ordinary wave function has one time variable and 3 n position variables. Now, that doesn't go so well with the concept of relativistic space-time. So you could either use this kind of wave function just on the time leaves, or because for solving the evolution of the wave function, you don't actually need the time foliation. You need it only later when you define the Bohmian trajectories. You can actually have a wave function that is defined in a completely covariant way, but then it is naturally suggested that your wave function should be a function of n space-time points. In this situation, then, the conventional wave function would be a function of n simultaneous space-time points, but now you would want to demand of these n space-time points merely that they're mutually space-like, but not that they're simultaneous. Good. So that means that each of these particle variables gets its own time coordinate, so you have a multi-time wave function. Now, for this multi-time wave function, you get multi-time equations. So if you have n time variables, you need n Schrödinger equations. Good. So this multi-time wave function is then a covariant particle position representation of the state vector. It's actually closely related to the Tomonaga-Schwinger wave function, but in fact simpler. Let me just quickly mention there's a certain consistency condition that these equations need to satisfy in order to be solvable. And these conditions are trivially satisfied for non-interacting particles, but don't work with interaction potentials, except when you have sort of delta potentials, zero-range interactions. They actually possess consistent multi-time evolution equations, or we've been able to set up consistent multi-time evolution for interaction through emission and absorption of bosons. Thank you very much for your attention.